Hello, in this session we are going to study some area calculations. In this specific case, we will focus on those areas enclosed between two functions. The objectives we pursue are to apply the definite integral for the calculation of areas determined between the graph of two functions and to properly interpret the results obtained by the definite integral. The necessary requirements are the calculation of primitives, the concept of the definite integral, and its relation with the area enclosed by the graph of two functions, and its relation to the area enclosed between a graph and the x-axis, and the understanding of the concept of the calculus enclosed by a function. Well, let's take it one bit at a time. Let's take two continuous functions like f and g. The continuity aspect of this is for convenience. It will help us avoid problems. Any other natural function can also be calculated using this process. Let's take our function f, and now let's take function g. We are interested in the area enclosed between these two. Now we are going to join the two graphs. Let's put them together. After performing these steps, we obtain the following image, which displays both graphs simultaneously. Our main focus lies in the region enclosed by these two graphs. From a functional perspective, this is a somewhat contrived exercise. It's merely an illustration of what's presented here. Typically, when calculating areas, we deal with regions defined by continuous functions. If we wish to calculate the area of a region bounded by continuous functions, then this methodology allows us to determine its area. But abstractly in mathematics, we take two continuous functions like these, and what we are interested in is to calculate the region determined by them. Normally, when we talk about the region determined by two functions and calculating its area, we refer to the region determined that is bounded, in other words, the region that can indeed be seen. We can see that to the right and to the left there would still be a given region, but that given region is infinite. It is not bounded, and therefore we are not sure, we do not know for sure that this area is finite, that is, that it has a finite area. Sometimes that can happen, but not always, so we will focus on the bounded one for now. Well, in this case, what is very clear is that we have a series of cutting points of the graphs that bound exactly that region. Therefore, if I want to calculate this area with integrals, it is clear that what I would have to do would be to integrate between a and c. What functions though? Well, that is a bit trickier. I would have to study what happens between a and b first. Where you notice that the function that is above is the f, and the function that is below is the g, and between b and c, where the roles are exchanged and the function g now becomes above, and the function f appears below. Well, let's see exactly how this area has to be calculated. We do know how to calculate the area enclosed between a graph and the x-axis. Let's turn this problem into exactly that, but how? Let's take a little bit of the graph and let's draw a new graph. We set the points where our problem is framed, A, B, and C, and what we are going to do is to take the region of which I want to calculate its area, and we are going to give vertical cuts in each of the values of x. First, I cut at A level. When cutting at A, as it is a point where the two functions meet, there is no area. That is, well, actually there is no length. Let's say that the segment that we just cut is simply a point. We transfer that to the new axis that is on the right. As we can see, in the height, I have put a segment of length 1. We cut at another value of x, and in this value of x, we are now cutting a segment a little bit bigger. We must take that segment value to the new graph, and what we do is the following. The end of the segment that touched the function g, which in this case is below, we take it to the x-axis. That is going to make that each one of these segments is upwards of the x-axis. We can do it with another one, with another one, with another one, with another one, and so on. We see that, as always, the end of the function g, which is the one that is below, we take it to the axis. In fact, what we are doing is to move all those segments towards the axis of the x, and they always stay above. And as you would expect, when I get to b, there's no cut, because there's no segment enclosed at that height. Now we are going to do the same thing for the other one. I go back to cut, 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 and it is now when we notice that the values come out below. Why does that even happen? Well, because now the function g, which was below, has moved above, and so the ends, the segments, when I move them, the end of g goes back to the x-axis, and so now the segment appears to be below. Well, I will keep doing this until I get right to the other end. Okay, so what we've just done is we've just converted the initial area that we had on the left into this area on the right side. The two areas are exactly the same, but now it's simply the area enclosed between the graph of a function and the x-axis, in which we might ask ourselves where the function is. Well, the function f of x minus g of x, the difference between the two. Then, in fact, any problem of two functions can always be reduced to the problem of a single function. Which one? Basically, the difference between the two. And as we already know, when we have the difference between the two, we have to be careful where that function cuts the x-axis. But we do observe that the cuts with the x-axis are exactly the points where the two functions, f and g, coincide. Well, once we have reduced the problem to a single function, the calculation of the area is very simple and straightforward. The area would simply be the integral of the absolute value of the function, or we could also calculate it by splitting it into smaller pieces. If we choose this last option, the very first chunk would be the integral between a and b of f of x minus g of x. And we observe that in this case the area is positive. Therefore, we would end up having f minus g. If we want to do the next slice now, the slice that goes from b to c, since now we are dealing with a negative, we would have to change the sign to the result. And that, in fact, what it does is, instead of having f minus g, what we would have is g minus f. Therefore, we are left with this integral we can see right here. The result of the area would be the sum of these two integrals. Let's pay attention to the fact that in the first one, what I do is the integral between a and b of the function that is above, which was f, minus the function that was below, which was g. And in the second of the integrals, I do exactly the same. The integral between b and c of the integral of the function that was above, which was g, and the function that was below, which was f. Let's wrap it up. This was it for today's session. Now we should be able to calculate simple integral areas with the definite integral, and to properly interpret the results that the definite integral gives us. Thank you for listening. See you in the next video.